Hello everyone, welcome to SleepSpace. Tonight we will talk about where your consciousness might go after death. For as long as humans have been able to think about themselves, we've wondered what happens at the end of life. It is a question that touches everyone, whether you are a scientist, a philosopher, or simply someone lying awake at night with curiosity about the mystery of existence. Consciousness, the feeling of being aware, of experiencing the world and recognizing yourself as a self, is one of the greatest puzzles science has ever tried to understand. Tonight, we're going to walk through the scientific perspectives, exploring what might happen to that fragile yet profound thing we call awareness, when the body ceases to function. Together, we will not seek supernatural answers, but instead rely on what physics, biology, and neuroscience can tell us. Yet, even within science, the possibilities can be as astonishing and awe-inspiring as any story ever told. To start, it's worth considering what we mean when we talk about consciousness. Neuroscientists often define it as the state of being aware of one's environment and of oneself. Philosophers sometimes expand the definition to include qualia, the raw feel of experience, like the redness of red or the warmth of a summer day. Whatever definition we use, consciousness is not just electrical signals firing in a vacuum. It is the subjective feeling of being alive. To ask where it goes after death is to ask what happens to the very essence of that feeling when the physical body breaks down. The most straightforward scientific perspective is that consciousness depends entirely on the brain. Billions of neurons communicate with each other through electrical and chemical signals, forming networks that process information, regulate perception, and create what we call the mind. According to this view, when the brain dies, the electrical activity that sustains consciousness stops, and with it, the experience of being. This is the dominant view in neuroscience, that consciousness is emergent from brain activity and cannot exist independently of it. In this model, when the body dies, consciousness simply ends, much like a flame extinguished when fuel runs out. But this answer, while clear, leaves many unsatisfied. After all, it's one thing to know that neurons stop firing. It's another to grasp why subjective experience exists at all. This is often called the hard problem of consciousness, a term coined by philosopher David Chalmers. The hard problem asks, why does information processing in the brain feel like something? Why doesn't it just happen silently, without any inner world? Science can map brain activity, track patterns of neurons, and even predict choices before people consciously make them. Yet it still struggles to explain why those processes are accompanied by the vivid experience of being alive. Because of this, even within a strictly scientific framework, there are several competing theories about the fate of consciousness after death. One influential approach is the integrated information theory, or IIT. According to IIT, consciousness corresponds to the amount of integrated information generated by a system. In other words, it arises when information is not just processed, but also linked together into a unified whole. Under this view, a brain is conscious because it integrates vast amounts of sensory input, memory, and internal states into one experience. When death occurs and integration breaks down, the theory suggests that consciousness disappears. However, IIT also raises fascinating questions. If consciousness is simply integrated information, then could other systems, perhaps artificial intelligence, or even the universe itself, also be conscious in some way? If so, then death may not mean the end of consciousness altogether, but rather the dissolution of one particular node of it. Another framework is global workspace theory, which compares consciousness to a theatre. In this metaphor, many unconscious processes occur backstage. but only a few pieces of information are spotlighted and broadcast to the entire system, becoming part of conscious awareness. According to this theory, when the brain is deprived of oxygen and neural activity fades, the spotlight shuts off and the play ends. Nothing is left to broadcast. Yet again, this highlights the dependence of awareness on brain activity, suggesting that the continuity of self is bound to the physical survival of the body. But physics adds another dimension. The brain does not exist in isolation. It is made of atoms, particles, and energy that follow the same rules as the rest of the universe. One of the most basic laws of physics is the conservation of energy. Energy cannot be created or destroyed, only transformed. When the body dies, its energy disperses into the environment. Heat radiates outward, chemical bonds break down, and atoms are recycled into new forms of life. Some scientists suggest that consciousness itself is not a separate kind of energy, but rather a process carried out by the brain. Yet the question arises, if consciousness is a process of physical matter and energy, does some trace of it persist in the transformations that occur after death? Not in the sense of memory or personality, but in the deeper sense of information. Here we arrive at the strange frontier where neuroscience meets physics, the role of information in the universe. Some physicists argue that information may be as fundamental to reality as matter or energy. The laws of thermodynamics describe how information interacts with entropy, the measure of disorder. In this context, the mind can be seen as an intricate pattern of information, one that decays after death. But patterns are not easily erased. Just as a wave leaves ripples in a pond after it passes, consciousness may leave traces in the physical systems it interacted with. Your thoughts, actions, and memories shape not only your brain, but also your environment. After death, while the unified experience of self disappears, the informational footprint you leave behind continues to ripple through the world in measurable ways. Of course, there are more speculative scientific explorations as well. Some researchers in quantum physics have suggested that consciousness might be linked to quantum processes in the brain. This idea, though controversial, is often associated with the work of physicist Roger Penrose and anesthesiologist Stuart Hameroff. They propose that microtubules within neurons could host quantum states, and that these states collapse in ways that give rise to consciousness. If this were true, then perhaps death does not mark an absolute end, but instead a transformation at the quantum level. Quantum states are notoriously strange. They can exist in superpositions, spread across space, and become entangled with distant particles. Some theorists have even wondered whether quantum consciousness might persist beyond death, diffused into the fabric of the universe. Most neuroscientists remain skeptical of this model, but it illustrates how the boundaries of science stretch when we attempt to answer the ultimate question of where consciousness goes. Medical research also provides intriguing, if puzzling, data. Near-death experiences, often reported by people revived after cardiac arrest, describe vivid perceptions of light, tunnels, or floating outside the body. While some interpret these as evidence of consciousness continuing beyond death, scientific analysis points to alternative explanations. When the brain is deprived of oxygen, unusual activity occurs. For example, bursts of gamma waves, the kind associated with heightened perception, can appear in the seconds after cardiac arrest. The brain, in its final moments, may generate intense experiences that people later recall as near-death visions. Rather than proving that consciousness survives, this suggests that the dying brain may produce extraordinary mental states, moments before it shuts down completely. Still, the persistence of brain activity after the heart stops challenges the simple idea of instant unconsciousness and opens questions about the gradual transition between life and death. So, where does all this leave us? From the neuroscientific point of view, consciousness arises from brain processes, and when those processes cease, consciousness as we know it ceases as well. From the perspective of physics, however, the patterns and information that made up a mind do not vanish entirely. They transform, disperse, and ripple outward into the larger universe. From a philosophical standpoint, the fact that subjective experience exists at all, something so intangible yet undeniable, means the question remains open in ways science cannot fully close. Consciousness may be deeply tied to the body, yet it may also reveal something more fundamental about the universe itself. Tonight, we will continue to explore these ideas in depth, not to settle the question, but to live inside it for a while. The end of life is not only a biological event, but also a doorway into the greatest mysteries of reality. By looking carefully at what science shows us, and by following the evidence with open curiosity, we can begin to imagine what it might mean for the story of awareness to reach its final page. Whether consciousness ends, transforms, or connects to something larger, the investigation itself brings us closer to understanding the fragile and astonishing nature of being alive. When we talk about what happens to consciousness after death, it is tempting to think of the moment of death as an instant, a sharp boundary line between being alive and no longer existing. In reality, the scientific picture is far more nuanced. Death, like birth, is a process rather than a single event. To understand where consciousness might go, we first need to understand how consciousness is measured, how the brain shuts down, and why even in those final moments, awareness can behave in unexpected ways. Scientists studying consciousness begin by facing a basic problem. We cannot directly observe another person's subjective experience. Instead, researchers rely on indirect measures, correlating brain activity with reports of awareness. In clinical settings, one of the most widely used tools is the electroencephalogram, or EEG. By placing electrodes on the scalp, researchers can record electrical signals produced by large groups of neurons. These signals are often rhythmic and organized into patterns called brain waves. Delta waves during deep sleep, theta waves in light sleep, alpha waves during wakefulness rhythms when relaxed but awake, beta waves during focused thinking, and gamma oscillations linked to high-level processing. Each of these rhythms reflects different states of consciousness. What matters for our discussion is that as the brain approaches death, these rhythms collapse often in a predictable sequence, but sometimes with unexpected bursts of activity. The medical definition of death is also not as simple as it may seem. Traditionally, death was defined as the moment the heart stopped beating. But modern medicine complicates this picture. With the development of resuscitation techniques, ventilators, and life support, the heart can be restarted or artificially maintained. For this reason, most medical and legal systems now define death in terms of the brain, specifically brain death, the irreversible loss of all brain activity. A person whose heart is beating on a ventilator can still be considered legally dead if there is no brain activity. This underscores the central scientific view. Without a functioning brain, consciousness cannot exist. Yet what exactly happens during the transition to brain death is not fully understood. Recent studies have revealed surprising findings. In 2013, researchers studying rats found that after cardiac arrest, the animals displayed a sudden surge of highly synchronized brain activity, lasting about 30 seconds. This activity was even more organized than during normal waking states. Some scientists have speculated that this surge may underlie reports of near-death experiences in humans, a final storm of neural activity producing vivid, dreamlike experiences before the complete shutdown. Other studies in humans have recorded persistent electrical activity minutes after the heart has stopped. These findings suggest that the brain's path into silence is not immediate, but rather a sequence of changes that may still generate fleeting moments of awareness. This opens an important question. If consciousness depends on the brain, does that mean awareness is simply a byproduct of neural activity, or could it reflect something deeper about the way information is processed? To approach this, scientists have developed experiments to measure consciousness in people who cannot communicate. For example, patients in comas or vegetative states are sometimes asked to imagine performing specific tasks, like playing tennis, while their brain activity is recorded. Astonishingly, some patients who appear outwardly unresponsive still show patterns of brain activation indistinguishable from healthy individuals when given such instructions. This has led to the realization that consciousness is not an all-or-nothing state, but can exist in varying degrees, sometimes hidden beneath silence. The idea of varying degrees of consciousness is central to modern theories. One of the most striking frameworks is integrated information theory, IIT, which we touched on earlier. IIT proposes a mathematical measure of consciousness called phi that quantifies how much information is integrated in a system. A high phi value suggests a rich, unified experience. A low phi value suggests minimal awareness. What makes this theory relevant to death is that it provides a way to think about the gradual fading of consciousness. As brain networks lose coherence and integration breaks down, phi decreases, eventually reaching zero when no information is integrated at all. In this view, death is not a sudden disappearance, but a continuous decline of integration, like the dimming of a light until it goes out completely. Another approach, global workspace theory, GWT, offers a different picture. In GWT, consciousness arises when information is broadcast across the brain's networks, making it available for decision-making, memory, and self-reflection. Without this broadcasting, information remains local and unconscious. In the context of death, as neurons lose the ability to coordinate and communicate, the global workspace collapses. Information may still exist in local pockets for a short time, but it never reaches the unified stage of awareness. Here again, death appears as a process of disintegration rather than an instant cutoff. Both theories raise a larger philosophical issue. Is consciousness an emergent property that exists only when certain physical conditions are met, or is it somehow fundamental to the structure of reality? The prevailing view in neuroscience is that it is emergent, like the liquidity of water, which arises from molecules interacting but is not present in the molecules themselves. Yet, unlike water, consciousness has the additional complication of subjectivity. This makes the scientific study of its disappearance at death a uniquely difficult problem. We can track activity, measure integration, and even detect hidden signs of awareness. But we cannot directly observe the transition from being to not being. Still, evidence from medicine and neuroscience gives us important clues. Consider what happens during general anesthesia. Drugs like propofol or ketamine alter brain activity in ways that can switch consciousness on and off. Patients under anesthesia often report no experience at all, a kind of gap in awareness, as though time did not exist for them. When they awaken, consciousness returns seamlessly, but with no memory of the gap. In some sense, death may resemble this, an irreversible version of anesthesia, where the brain can no longer restore the global patterns necessary for awareness. This analogy highlights the fragility of consciousness and its reliance on precise neural dynamics. But unlike anesthesia, death involves not just temporary suppression, but the complete breakdown of the physical substrate. Neurons depend on oxygen and glucose to function. Without them, ion gradients collapse, membranes lose integrity, and electrical signaling stops. In the hours and days that follow, cells die, synaptic connections dissolve, and the intricate architecture of the brain disintegrates. From the perspective of neuroscience, this means the structures that supported consciousness are permanently lost. Whatever consciousness was, it cannot persist without this biological infrastructure. Yet the story is not finished. Physics reminds us that while the biological structures vanish, the matter and energy do not. The atoms in the brain disperse, the heat radiates outward, and the chemical bonds break down into simpler molecules. On one level, consciousness seems gone. On another, the raw ingredients that once supported it continue to exist in new forms. From this perspective, death is not annihilation, but transformation. The question is whether consciousness itself transforms, or whether only its physical basis does. Most scientists argue the latter, but the distinction is crucial. It points to the boundary of what science can currently explain. We can trace the fate of molecules and energy, but tracing the fate of subjective experience is far more elusive. Another fascinating line of research concerns the persistence of brain activity after cardiac arrest. In 2023, a study monitoring patients who died in intensive care units reported surges of gamma activity in some individuals minutes after life support was withdrawn. These gamma bursts were similar to those seen during dreaming and memory recall. While it is impossible to know whether patients were conscious during these moments, the findings suggest that the brain may generate organized activity even in the face of impending shutdown. This complicates our picture of death. It may involve brief windows where consciousness flickers, even as the body fails. For those who wonder where awareness goes, this suggests the transition is more complex than a simple off switch. These insights also highlight the importance of defining what exactly we mean by the end of consciousness. If by consciousness we mean the ongoing subjective experience of self, then brain death likely marks its end. But if we broaden the concept to include the information encoded in neural patterns, then something of consciousness persists, even if not in a way we would recognize as awareness. Every memory, every habit, every trace of personality is a pattern inscribed in the brain's connections. When the brain decomposes, those patterns scatter into the environment. They no longer form a unified self, but they do not vanish without a trace. What emerges from all of this is a picture of death as both an ending and a transformation. From the perspective of neuroscience, the unified experience of being ceases when the brain can no longer sustain integration and communication. From the perspective of physics, the matter and energy continue, dispersed into the universe. From the perspective of information theory, patterns dissolve but leave echoes. Each perspective captures part of the story, though none provides the complete answer to the question of where consciousness goes. This is precisely why the scientific exploration of death remains one of the most profound frontiers of human inquiry. Physics deals not only with matter and energy, but also with information, the patterns and relationships that shape reality. In fact, some scientists argue that information is as fundamental to the universe as space, time, and energy. If that is true, then perhaps the patterns that make up consciousness leave traces beyond the biological life of the brain. To explore this possibility, we need to consider the laws of thermodynamics, the conservation of energy, and the way information interacts with matter. One of the most powerful principles in physics is the conservation of energy. Energy cannot be created or destroyed, only transformed. When a living body dies, the chemical energy in cells is not lost. It is released as heat, consumed by microbes, and eventually recycled into other forms. Atoms do not vanish when biological processes stop. They disperse into the environment, becoming part of soil, air, and future life. This is a physical certainty. The deeper question, however, is whether consciousness is reducible to these physical forms of energy, or whether it represents a kind of information structure that transcends simple material processes. To explore this, consider entropy, the second law of thermodynamics. Entropy is often described as disorder, but more precisely, it is a measure of the number of ways a system can be arranged. Low entropy means a highly ordered system. High entropy means many possible configurations with no particular structure dominating. Living systems, including the brain, are extraordinary because they maintain extremely low entropy compared to their environment. The brain is not a random collection of molecules. It is an exquisitely ordered system that channels energy to create and preserve patterns of activity. Consciousness may be understood as one of the emergent properties of this highly ordered, low-entropy structure. At death, entropy increases. The ordered patterns of neurons, synapses, and electrical activity collapse into more disordered states. From this perspective, consciousness is lost not because energy disappears, but because the ordered patterns that supported awareness decay into noise. This aligns with the view of many neuroscientists. The self is not energy itself, but a specific arrangement of matter and energy. When that arrangement breaks down, the subjective sense of being ends. Yet entropy does not mean information is obliterated entirely. Information can transform, scatter, and be embedded into the environment. In physics, information is surprisingly resilient. In fact, the role of information in physics has been at the center of some of the most profound scientific debates. Consider the black hole information paradox. According to general relativity, anything that falls into a black hole is lost forever. But according to quantum mechanics, information cannot be destroyed. This tension has led physicists like Stephen Hawking to propose that black holes must somehow preserve the information of what falls into them, even if in scrambled form. While black holes may seem remote from the question of consciousness, the principle is the same. The universe does not allow information to simply vanish without a trace. If information is fundamental, then the patterns that made up a conscious mind cannot be erased entirely. They must transform into new forms of information within the fabric of reality. This idea is not just philosophical speculation. Physicist John Wheeler once suggested that it from bit could be the foundation of physics. The notion that every physical entity, every particle, every force, even space-time itself, arises from binary choices or bits of information. In this view, the universe at its core is not material but informational. If that is the case, then consciousness, as a complex informational process, may not be separate from reality's foundation, but woven into it. Death, then, might not mean the destruction of consciousness as information, but its redistribution into the broader network of reality. The link between consciousness and information has also been explored through neuroscience. Memories, thoughts, and personality traits can all be described as information encoded in the brain's connections. Synapses strengthen or weaken through learning, storing patterns of experience as structured networks. From one perspective, consciousness is the dynamic use of this stored information in real time. When the brain ceases to function, these networks dissolve, but the information they carried may already have spread outward. Every word spoken, every action taken, every influence on other people is an externalization of internal patterns. In this sense, the informational content of a life persists beyond the biological body, though not as subjective awareness. Yet physics offers an even stranger possibility. Quantum theory, the most successful framework in modern science, suggests that reality at its deepest level is probabilistic and governed by information. Quantum systems can exist in superpositions where multiple outcomes coexist until measurement. They can also be entangled such that the state of one particle depends on the state of another, no matter how far apart they are. Some researchers have speculated that consciousness itself may involve quantum processes, though this remains controversial. If true, it raises the possibility that death does not eliminate consciousness entirely, but allows its quantum informational structure to diffuse into the larger quantum field. Even if mainstream science treats such ideas with skepticism, they illustrate the difficulty of drawing a firm line between consciousness and the fabric of physical reality. Another way to think about this is through the concept of complexity. The brain is one of the most complex structures known in the universe, with about 86 billion neurons and trillions of synaptic connections. Complexity science studies how simple interactions can give rise to emergent properties, patterns that cannot be reduced to their parts. Examples include the flocking of birds, the self-organization of ant colonies, or the turbulence of fluids. Consciousness, many argue, is an emergent property of the brain's extraordinary complexity. At death, this complexity disintegrates, but the principle of emergence suggests that once consciousness has arisen, it leaves imprints that extend beyond the system itself. Human ideas, language, technology, and culture are all examples of consciousness extending itself outward. In this sense, while the unified conscious self dissolves, the emergent patterns it produced do not vanish, but become part of the larger web of human and physical systems. This brings us to one of the most provocative questions in physics and philosophy. Is information ever truly lost? If not, then consciousness, understood as an informational structure, cannot vanish completely. The second law of thermodynamics dictates that order decays into disorder, but even in high entropy states, traces of the original order remain. The ash of a burned book no longer contains readable words, yet in principle, the information about the words is still encoded in the arrangement of atoms and molecules in the smoke and residue. It is scrambled beyond recognition, but not annihilated. Could consciousness be similar? When the brain dies, the coherent patterns of awareness scatter, but the information they embodied continues in altered form, diffused into the environment. This is where physics challenges our intuitive sense of finality. From the everyday human perspective, death feels like a total end. From the perspective of information theory, however, the end may be more like a transformation, a shattering of a pattern into smaller fragments that persist in the universe. The subjective experience of self disappears, but the informational traces remain. This view is not comforting in the traditional sense, since it does not imply the survival of personal identity or memory. Yet it does suggest that consciousness, as an informational phenomenon, is part of the universe's larger informational flow. In this way, death is less a disappearance and more a diffusion. It is worth noting that many cutting-edge theories of physics treat information not just as an abstract concept, but as something physically real. For example, quantum information theory treats information as a resource that can be manipulated, transmitted, and conserved. Entanglement, teleportation, and quantum computing all depend on the physical reality of information. If consciousness is fundamentally informational, then its fate after death is not annihilation, but redistribution. Much like any other physical resource, the specific subjective experience ends, but the informational content disperses into the physical world. What makes this perspective so compelling is that it aligns with both neuroscience and physics while leaving room for mystery. Neuroscience shows us that consciousness depends on the brain's organization and ends when that organization collapses. Physics shows us that the patterns and information that once existed cannot be destroyed, only transformed. Together, these suggest that death is both an end and a continuation. An end of subjective awareness, but a continuation of informational patterns within the universe. Whether those patterns can ever reassemble into consciousness is another question, one that science cannot yet answer. Perhaps the most profound implication is that consciousness may not be something separate from the universe, but a way the universe organizes itself. In this sense, the question of where consciousness goes after death may be misframed. Consciousness may not go anywhere, because it was never a detachable object to begin with. It is an emergent process of matter and energy arranged in a particular way. When that arrangement ends, the process ceases, but the underlying matter, energy, and information remain. They continue to participate in the universe's ongoing dance of transformation. And yet, even within this strictly scientific framework, there is awe. To think that the mind is made of patterns of information and that those patterns ripple outward into the universe is no less astonishing than any story of an afterlife. Each thought you have, each word you speak, each influence you exert is a thread woven into the fabric of reality, persisting long after your own subjective awareness ends. Death, in this view, is not erasure, but diffusion, the scattering of one pattern into countless others, carried forward by the fundamental laws of physics. If consciousness depends on the brain, then to understand where it might go after death, we must understand how the brain behaves as life comes to an end. In many ways, the dying brain is as mysterious as the living one. For centuries, people assumed that when the heart stopped, the mind stopped instantly. Modern research shows that this is not quite true. The brain undergoes a remarkable and complex transition in the moments surrounding death. This transition is not only gradual, but it may also include surprising bursts of activity, suggesting that the last moments of consciousness are far from silent. The human brain is an organ of staggering complexity, consuming about 20% of the body's energy despite weighing only 3 pounds. Neurons depend on a steady supply of oxygen and glucose to maintain their electrical signals. These signals are made possible by delicate chemical gradients across cell membranes, maintained by pumps that expend energy. The moment the heart stops, the flow of oxygenated blood ceases and the brain is thrown into crisis. Energy supplies run down quickly, ion gradients collapse, and within seconds, electrical signaling falters. One might expect that awareness vanishes immediately. Yet evidence shows that the process is more layered. In the first 10 to 20 seconds after cardiac arrest, brain activity does not simply flatline. Instead, it undergoes a cascade of changes. Studies of animals have revealed that neurons may fire in a highly synchronized way during this window, producing waves of activity even stronger than those seen in wakefulness. In 2013, researchers at the University of Michigan recorded this phenomenon in rats, observing surges of gamma activity. oscillations typically linked to perception, attention, and memory. Such findings suggest that the brain's final moments may involve heightened states of integration, a kind of brief, intensified awareness before shutdown. Though we cannot directly access subjective reports in animals, parallels in human cases raise fascinating possibilities. In human studies, similar bursts of gamma activity have been recorded in patients as life support is withdrawn. These patterns sometimes resemble those seen during dreaming or memory recall. It is tempting to connect this to near-death experiences, reports of vivid visions, tunnels of light, or life reviews that people describe after being revived from cardiac arrest. While cultural interpretations vary, the scientific explanation may lie in the brain's last surge of activity. Starved of oxygen and overwhelmed by chemical imbalances, the brain may enter a hyperexcited state, producing powerful but transient experiences. From a strictly biological perspective, these final moments represent the last flicker of the neural machinery that generates consciousness. The phenomenon of a life review is particularly intriguing. Some people who survive cardiac arrest describe seeing vivid memories flash before them, often in a rapid, panoramic sequence. Neuroscience offers potential explanations. Memory is not stored in a single place, but distributed across networks of the brain, especially in the hippocampus and cortex. Under extreme stress, neurotransmitters like glutamate may flood synapses, destabilizing normal signaling, but also triggering widespread activation. This could unleash memory networks in an uncontrolled burst, producing the sensation of one's life unfolding all at once. Though speculative, this idea shows how the dying brain might generate experiences that feel profoundly meaningful. Other near-death phenomena, such as feelings of floating outside the body or moving through a tunnel, can also be linked to brain processes. Out-of-body sensations are associated with the temporoparietal junction, a brain region that integrates sensory signals about the body's position. When disrupted, as in seizures or artificial stimulation, this area can produce vivid illusions of floating or detachment. Similarly, tunnel visions may arise from changes in the retina and visual cortex. As oxygen levels drop, peripheral vision fades first, leaving only a bright central field, which can appear as a tunnel of light. These explanations do not diminish the significance of such experiences. They highlight how the brain itself can generate striking perceptions, even on the brink of death. Yet there is still much we do not know. One of the most surprising findings in recent years is the persistence of brain activity minutes after the heart stops. In 2022, doctors monitoring patients in intensive care reported organized electrical patterns occurring long after circulation ceased. These patterns included oscillations associated with cognitive processing. Although we cannot know whether these corresponded to consciousness, they suggest that the boundary between life and death is more blurred than previously thought. Consciousness may fade gradually, with intermittent sparks, rather than shutting off like a switch. This raises profound questions about how long awareness may linger in the dying brain. The concept of brain death adds further complexity. Brain death is defined as the irreversible loss of all brain function, including the brainstem, which controls basic reflexes like breathing. Clinically, this is the point at which a person is declared dead, even if machines can keep the heart beating. But determining irreversibility is difficult. Cases exist where patients in deep comas or vegetative states have shown hidden signs of awareness when tested with advanced imaging. For example, functional MRI studies have asked apparently unresponsive patients to imagine playing tennis. Remarkably, Some produce brain activity indistinguishable from that of healthy individuals following the same instruction. Though rare, such findings reveal that consciousness can persist in states where it seems absent. They remind us that measuring awareness is not straightforward, and that the line between life, death, and consciousness is not always clear. This has implications for how we think about the final fate of awareness. If consciousness is tied to complex patterns of neural activity, then the gradual loss of those patterns during death implies a gradual fading of consciousness. But it also means that in the moments of decline, there may be unexpected bursts or fragments of experience. What is it like to inhabit those moments? Science cannot answer directly, but the evidence suggests they may be vivid, strange, and perhaps even profound. The dying brain is not silent. It is dynamic, unpredictable, and capable of generating experiences that leave a lasting mark on those who return from the brink. Another layer of complexity arises when we consider memory and its relationship to death. Memories are stored in distributed networks of synapses, but they are also dynamic, constantly being updated and reshaped. In death, these networks degrade as cells lose their structural integrity. From a purely scientific standpoint, the personal history of an individual is lost when the brain decays. Yet memory is not confined to the brain alone. It is externalized through language, writing, art, and influence on others. While the subjective experience of memory disappears, the informational patterns it created continue to exist in the world. In this way, consciousness leaves behind echoes, even if the inner awareness no longer persists. From a medical perspective, studying the dying brain is not only a matter of curiosity, but also of ethics and care. Understanding how consciousness fades can inform decisions about end-of-life care, pain management, and the timing of organ donation. If awareness lingers longer than assumed, it raises questions about the subjective experience of patients in those final moments. Research in this area is still emerging, but it underscores the importance of approaching death not as an instantaneous event, but as a complex transition, both biologically and experientially. For neuroscience, the study of death is also a way of probing the very nature of consciousness. The fact that experiences can arise during the breakdown of the brain challenges simplistic views of awareness as either fully present or entirely absent. Instead, consciousness appears to exist on a spectrum, with different states emerging depending on the dynamics of neural networks. Death represents the far end of this spectrum, where organization collapses. But the journey there may reveal important clues about how consciousness works in life. What emerges from this scientific perspective is a view of death not as an abrupt void, but as a sequence of transitions. The brain fights to maintain function, surges into hyperactivity, and then gradually falls silent. Along the way, it may produce unusual experiences that, for those who return, feel transformative. For those who do not return, the story ends with the dissolution of the brain structure, and with it, the end of subjective awareness. Yet even here, the legacy of consciousness persists in the physical and informational traces left behind. The dying brain may be mortal, but the ripples it creates extend outward, shaping the world beyond the individual's final breath. This scientific lens may not answer the ultimate question of where consciousness goes, but it provides a clearer picture of how it ends. Awareness depends on fragile patterns of activity sustained by delicate balances of energy and matter. Death disrupts those balances and the patterns dissolve, yet in their dissolution, they leave evidence, data, and influence, traces that science can measure and that humanity can feel. Consciousness does not vanish into nothingness. It transforms, disperses, and echoes. The brain's final act is not silence, but a transformation, written in electrical storms, memory fragments, and informational ripples. When scientists describe consciousness as emergent, they mean it arises from the interaction of simpler components that on their own are not conscious. The classic example is water. Neither hydrogen nor oxygen is wet, but together they produce the phenomenon of wetness. Consciousness may be similar. Neurons are electrochemical cells that fire or rest depending on inputs. Alone, they are not conscious. Yet when billions of them interact through trillions of connections, new properties emerge. Among those properties is awareness, the unified sense of experience. Emergence is a cornerstone of complex system science. It explains why ants, though simple individually, can form colonies with collective intelligence capable of building intricate tunnels and regulating food supplies. It explains how simple mathematical rules, iterated over and over, can create fractal structures of breathtaking complexity. Consciousness, from this perspective, may be the ultimate emergent phenomenon. It is the product of interactions so rich and dynamic that a new layer of reality appears, the subjective world. Neuroscientists often illustrate this idea with network dynamics. The brain is not a static structure, but a constantly shifting web of connections. Neurons communicate through spikes of electricity and bursts of neurotransmitters, forming patterns that synchronize and desynchronize depending on context. These patterns can be studied at different scales. Local circuits that process specific sensory inputs, larger networks that integrate information across regions, and global oscillations that link the whole system together. Consciousness seems to emerge when these scales align in a way that supports integration without chaos, a delicate balance of order and variability. One influential framework is the Integrated Information Theory, IIT, proposed by neuroscientist Giulio Tononi. IIT attempts to quantify how much a system is conscious by measuring the degree to which its information is both differentiated and integrated. A system with many possible states but no integration, like a digital camera sensor, is rich in data but not conscious. A system with perfect integration but no differentiation, like a single light bulb that is either on or off, is unified but trivial. Consciousness, IIT suggests, exists in the sweet spot, where information is both highly varied and tightly integrated into a whole. According to this theory, the brain is conscious because it achieves an exceptionally high degree of integrated information. Death, by contrast, is the loss of integration, as networks fragment and collapse. Computational models have given further support to this view. Simulations of neural networks show that when connectivity reaches certain thresholds, the system begins to exhibit features of conscious processing, such as global accessibility of information and the ability to flexibly shift attention. These models also reveal fragility, reduce connectivity too much, and the system loses coherence. This is precisely what happens in brain injury, anesthesia, or death. Consciousness depends not just on activity, but on the right kind of activity: complex, integrated, and dynamic. Emergence also helps explain the unity of consciousness. Every moment of awareness feels like a coherent whole, even though the brain is processing countless signals in parallel. You do not experience color, sound, and memory as separate fragments, but as one seamless scene. This binding problem, the question of how disparate signals unify, has puzzled philosophers for centuries. Emergence offers an answer. When local signals become coordinated at the system level, a new layer of organization arises, giving rise to the sense of a unified perspective. When death dismantles that organization, the unity dissolves. The idea of consciousness as emergent has profound implications for the question of what happens after death. If consciousness depends on complexity, then when complexity ends, so does awareness. Just as wetness vanishes when water evaporates, subjective experience may vanish when the brain's networks disintegrate. From a scientific standpoint, this is the simplest explanation. The emergent phenomenon ceases when the system that generates it ceases. Yet this view also raises new questions. Is emergence entirely dependent on biological matter, or could it occur in other substrates, such as artificial systems? Could consciousness, in principle, be reconstituted if the right patterns of information were restored? Artificial intelligence research touches on this possibility. While today's AI systems do not exhibit consciousness, they demonstrate how complex behavior can arise from simple units. Neural networks in machines are inspired by the structure of the brain, albeit in much simpler forms. As these networks grow larger and more interconnected, some scientists speculate that emergent properties resembling consciousness could eventually appear. This raises a provocative point. If consciousness is truly emergent, then death may not be the end of consciousness in a universal sense. It may be the end of one particular instantiation of consciousness in one particular system, the human brain. But the principles of emergence could allow awareness to arise again, in different forms or different substrates. From a biological standpoint, though, the end of an individual's brain is the end of that individual's emergent consciousness. Complexity collapses through several mechanisms. First, the loss of energy supply disrupts synaptic communication. Neurons depend on sodium-potassium pumps to maintain gradients, and without oxygen, these pumps fail. Second, neurotransmitter imbalances flood networks with uncontrolled activity, destabilizing integration. Third, structural breakdown follows as membranes rupture and proteins denature. The result is not a clean shutdown, but a disintegration of patterns. What once supported rich, unified awareness becomes scattered noise. Emergence requires order within complexity. Death transforms that order into entropy. The concept of entropy is central here. In physics, entropy is a measure of disorder. Living systems, including brains, maintain low entropy by constantly consuming energy to create and sustain order. Death is, in essence, the loss of this struggle. As the body stops maintaining gradients and repairing damage, entropy rises. Order dissolves into randomness. In emergent terms, this means the higher level properties, such as consciousness, can no longer be sustained. They are not destroyed in the sense of being annihilated, but simply cease to exist because the conditions for their existence are gone. One might compare this to a whirlpool in a river. The whirlpool is a pattern of water constantly renewed by the flow. When the flow stops or changes, the whirlpool disappears. Nothing has gone anywhere. The pattern has simply dissolved. Consciousness, on this view, is like the whirlpool, a dynamic pattern of neural activity sustained by energy flow. When the flow ceases, the pattern cannot persist. Where does it go? Nowhere. It is not a thing, but a process, and when the process ends, the phenomenon ceases. Still, this raises the question of whether emergence could allow some form of persistence. Patterns, after all, can be preserved if the conditions that sustain them are maintained. In physics, waves can propagate across mediums, carrying information. Could consciousness, as a kind of informational pattern, be preserved or transferred? Most neuroscientists would argue no, at least in the sense of personal survival. Consciousness is not just information, but information embodied in a particular living system. Once the biological substrate is gone, the emergent property tied to that system is gone as well. Yet the idea is not entirely closed. Some researchers in digital preservation and brain emulation speculate about whether the informational structure of a brain could be mapped and replicated, allowing consciousness to re-emerge. Though speculative, this illustrates the power of the emergent framework. It opens the door to seeing consciousness not as a fixed essence, but as a pattern tied to complexity. The emergent view also clarifies why certain states diminish consciousness without destroying it. In anesthesia, drugs disrupt integration among brain networks, lowering the system's complexity. Patients become unconscious, but the brain still functions, and the complexity can return when the drug wears off. In deep sleep, connectivity patterns shift, reducing integration, yet consciousness returns upon waking. Death differs because the collapse of complexity is irreversible. Once the structure disintegrates, the conditions for emergence cannot be restored. This perspective challenges some intuitions about selfhood. If consciousness is emergent, then the self is not a separate entity residing in the brain, but an emergent property of brain dynamics. The sense of continuity, the feeling that I am the same person today as yesterday, arises from stable patterns maintained over time. Death interrupts this continuity by dismantling the patterns. From a scientific standpoint, what ends is not an immaterial soul, but the ongoing process that gave rise to the experience of selfhood. However, emergence does not diminish the significance of consciousness. On the contrary, it highlights how extraordinary it is. Billions of cells, none of which are conscious, collectively generate the feeling of being alive, aware, and reflective. This is an achievement of nature that is rare, delicate, and astonishing. Death, in this view, is not the disappearance of something trivial, but the collapse of one of the most remarkable emergent structures in the known universe. This framework also helps bridge the gap between biology and physics. Consciousness as emergent links the material substrate of neurons with the abstract property of awareness. It shows how subjective experience can arise from physical interactions without requiring anything beyond them. At the same time, it leaves room for wonder. How can patterns of matter and energy give rise to something as profound as the feeling of existence? The answer lies in complexity, in the way systems transcend their parts to create wholes with new properties. Consciousness is generated by the brain, which is made of matter and energy, both of which obey physical laws. Physics is the science of the fundamental rules that govern these building blocks. If consciousness ends at death, it does so within those rules. If it transforms in some way, physics must be consistent with that transformation. To approach the question scientifically, we must ask, what happens to the physical basis of consciousness when a living system dies? The first principle to consider is the conservation of energy. Energy in a closed system cannot be created or destroyed. Instead, it changes form. Kinetic energy becomes heat, chemical energy becomes electrical signals, and so forth. The brain consumes about 20 watts of power during wakefulness, roughly equivalent to a dim light bulb. This power comes from glucose metabolism, which converts chemical energy into the electrical activity of neurons. When the body dies, the chemical reactions that sustain brain activity cease, and energy is no longer directed into maintaining neural signals. Instead, energy dissipates into the environment as heat. Conservation of energy tells us that nothing disappears. The energy that once powered consciousness spreads outward. But while energy persists, the organized patterns that constituted awareness do not. Energy alone is not consciousness. Consciousness depends on the precise organization of that energy into meaningful patterns of neural activity. Death disrupts this organization, transforming structured dynamics into unstructured noise. The distinction between energy and organization brings us to entropy. Entropy is the measure of disorder in a system. Living organisms, including human brains, are remarkably low entropy systems. They maintain order by consuming energy and exporting disorder into their surroundings. This constant battle against entropy allows complex processes, including consciousness, to persist. When the body dies, this battle ends. Entropy increases as molecular structures break down, membranes rupture, and gradients collapse. The physical matter remains, but the low entropy patterns that sustained awareness disintegrate. From the perspective of thermodynamics, death is the transition from an ordered state capable of supporting consciousness to a disordered state that cannot. The arrow of time, another concept from physics, deepens this picture. Time, as we experience it, flows in one direction, from past to future. This arrow is defined by the increase of entropy. Systems evolve from order to disorder. Consciousness, in many ways, is an experience of navigating this arrow, constructing a sense of continuity as the brain organizes incoming information into coherent narratives. When the brain's order collapses, the subjective arrow of time also ends. Consciousness does not continue forward in subjective experience because the mechanism that generates temporality no longer functions. Death is therefore not only the end of awareness, but also the end of time as experienced by that awareness. From within, it is not an event followed by nothingness. It is simply the end of events altogether. This scientific framework helps clarify why consciousness does not go anywhere after death, in the same way that a whirlpool does not go anywhere when the water stops flowing. Consciousness is a process, not a substance. It is the organized dynamics of matter and energy. Once those dynamics collapse, the process ceases. What persists are the raw materials, atoms, molecules, energy, but not the emergent property we recognize as awareness. Just as music ends when the vibrations stop, consciousness ends when the patterns stop. Yet physics also opens doors to deeper questions. Consciousness depends on physical processes, but it is not obvious how subjective experience arises from them. This is known as the hard problem of consciousness, posed by philosopher David Chalmers. Why should physical processes give rise to experience at all, rather than functioning without it? Some physicists and philosophers suggest that consciousness may not merely be a product of matter, but a fundamental feature of the universe alongside space, time, mass, and charge. While speculative, this view, sometimes called Panpsychism, argues that the building blocks of matter may possess primitive forms of awareness, which combine into more complex consciousness in brains. If this were true, then death would represent not the annihilation of consciousness, but the dissolution of a particular configuration back into more fundamental forms. Physics does not confirm this view, but it does not rule it out either. Quantum physics adds another layer of intrigue. Quantum systems are governed by probabilities, superpositions, and entanglements that defy classical intuition. Some researchers, such as physicist Roger Penrose, have suggested that consciousness may be linked to quantum processes in the brain. His hypothesis, known as ORC-OR, orchestrated objective reduction, proposes that quantum states in microtubules within neurons contribute to awareness. Critics argue that the brain is too warm and noisy for delicate quantum states to survive, but new research shows that biological systems can exploit quantum effects, as in photosynthesis and bird navigation. If quantum processes are involved in consciousness, the fate of awareness after death might be tied to quantum decoherence, the collapse of quantum states into classical outcomes. Death, in this view, would scatter quantum coherence into the environment, ending the organized processes that sustain subjective experience. Still, it is important to be cautious. Quantum theories of consciousness remain highly speculative, and most neuroscientists explain awareness through classical processes of neural networks. Nevertheless, the role of quantum physics highlights an essential point. Consciousness is tied to the fundamental laws of the universe. Whatever it is, it must conform to those laws. When life ends, the matter and energy that supported awareness persist, redistributed according to the rules of thermodynamics and quantum mechanics. Consciousness, understood as an emergent process, ceases because the structure that maintained it no longer exists. Cosmology, the study of the universe at large, also shapes our understanding. The atoms in our brains were forged in stars billions of years ago, assembled through cosmic processes long before life appeared. After death, those atoms return to the cycles of nature, eventually rejoining the cosmos that created them. From this perspective, consciousness does not vanish into nothingness, but dissolves back into the universe. The subjective experience ends, but the physical material that made it possible continues its journey, perhaps one day becoming part of new systems that generate new forms of awareness. While this does not preserve individual consciousness, it situates each life as part of a grand cosmic cycle of matter and energy. Physics also emphasizes the universality of laws. The same principles that govern the motion of galaxies also govern the firing of neurons. This unity suggests that consciousness is not outside the natural order, but deeply embedded within it. Death is therefore not an exception to the laws of physics, but an expression of them. The dissolution of awareness follows the same rules that shape stars, black holes, and the expansion of the universe. Consciousness is remarkable, but it is not exempt from entropy. Some have speculated about whether the universe itself might be conscious, or whether consciousness could play a role in the fundamental fabric of reality. While intriguing, these ideas remain speculative and are not part of mainstream physics. What is clear is that physics provides boundaries within which any explanation of consciousness must fit. Whatever happens after death, it must be consistent with conservation laws, thermodynamics, and cosmology. So far, the simplest explanation is that consciousness, as an emergent process of brain dynamics, ends when those dynamics cease. Yet this does not make consciousness trivial. On the contrary, the physical framework reveals its rarity and fragility. The universe is vast and mostly lifeless. Out of countless arrangements of matter, only a tiny fraction sustain the low entropy conditions necessary for consciousness. Each conscious life is therefore a rare configuration of the cosmos, fleeting but extraordinary. Death, seen through physics, is the reversion of that rare configuration back into the more typical state of disorder. Awareness does not travel elsewhere, it ceases, but its existence, however brief, is a remarkable phenomenon of physics itself. From this perspective, asking where consciousness goes after death may be the wrong question. Consciousness is not a substance that can travel. It is a state of matter and energy, a process sustained by complexity. When that complexity ends, the state ceases. What remains is the matter and energy, redistributed into the universe. The process does not go anywhere, it simply ends. Yet the materials remain, and the laws of physics ensure that they will continue to play roles in the ongoing story of the cosmos. In sum, the physics and cosmology perspective shows that consciousness depends on ordered energy and matter, sustained against entropy by the flow of time. Death ends this order, redistributes energy, and returns matter to the cosmos. Consciousness does not survive as an ongoing process, but neither is it erased from reality. Its physical basis transforms, its patterns dissolve, and its materials continue. The emergent process ceases, but the universe that made it possible carries on, shaping new forms, perhaps even new consciousnesses, in the unfolding of time. Modern medicine has extended the boundary between life and death in ways unimaginable a century ago. Where once cardiac arrest meant certain death, resuscitation techniques now make survival possible, minutes, sometimes hours, after the heart stops. This ability to pull people back from the brink has opened a unique scientific window into what happens to the brain as life ends. By studying survivors of cardiac arrest and monitoring patients during the dying process, researchers are piecing together one of the most profound mysteries in science. What happens to consciousness in the moments surrounding death? One of the most striking tools for this investigation is cardiopulmonary resuscitation, or CPR. Developed in the mid-20th century, CPR combines chest compressions and artificial ventilation to keep oxygen flowing to the brain after cardiac arrest. When performed promptly, it can preserve neural function long enough for advanced treatments, defibrillation, medications, or cooling therapies to restart the heart. The fact that people can sometimes be revived after 10 or more minutes of apparent death challenges the older idea that consciousness ceases instantly when the heart stops. Instead, it suggests a transitional period, during which awareness may fluctuate in unexpected ways. Research confirms that the brain can remain active during this period. Electroencephalogram (EEG) studies have recorded organized brain waves for up to 30 seconds after cardiac arrest. In some cases, bursts of high-frequency gamma activity, linked in waking life to perception and memory, emerge just as circulation ceases. These findings raise the possibility that brief episodes of heightened awareness may occur even as the body is shutting down. From a clinical standpoint, this has major implications. Patients thought to be unconscious may still be experiencing something, even if fleeting and fragmented. Near-death experiences, often reported by cardiac arrest survivors, add another layer of evidence. Around 10 to 20% of people who survive resuscitation describe vivid mental events during the time they were clinically dead. These experiences include sensations of detachment from the body, encounters with deceased relatives, feelings of peace, or a panoramic review of life events. While interpretations vary culturally and personally, from a medical perspective, these reports provide valuable data. They suggest that conscious-like activity can persist even when traditional signs of life are absent. One of the most comprehensive studies of this phenomenon is the AWARE study, Awareness During Resuscitation, led by Dr. Sam Parnia. This multi-hospital project interviewed hundreds of cardiac arrest survivors to document experiences during clinical death. A small percentage reported verifiable perceptions, such as recalling conversations or events in the hospital room, suggesting that awareness, or at least sensory processing, can persist for short intervals after cardiac arrest. While rare and controversial, these accounts challenge the assumption that consciousness ends abruptly when the heart stops. They imply that under certain conditions, fragments of experience may survive the initial collapse of circulation. How is this possible? The brain's response to oxygen deprivation offers clues. Within seconds of cardiac arrest, electrical activity drops, but the brain does not instantly become inert. Cells begin to depolarize as ion gradients collapse, but this process takes minutes to fully unfold. During this window, abnormal but organized patterns of activity can arise. Stress hormones and neurotransmitter surges may further amplify the brain's excitability, producing vivid experiences. The tunnel vision, bright lights, or feelings of euphoria described in near-death accounts can all be linked to specific neurophysiological processes: retinal ischemia, temporoparietal disruption, or endorphin release. These explanations do not diminish the power of the experiences, but root them in the biology of the dying brain. Recent advances in monitoring have extended this knowledge. In 2022, researchers observed a patient's brain activity as they died under continuous EEG. Unexpectedly, the brain showed patterns of organized oscillations for over 30 seconds after cardiac arrest, including gamma rhythms consistent with cognitive processing. Though a single case, it confirmed that the brain can remain active at the very edge of death. Other studies have noted similar activity in animals, suggesting that it is a general feature of mammalian brains. This finding reshapes our understanding of death, not as a sudden event, but as a process in which consciousness may taper gradually. The clinical implications are profound. If awareness can linger, even briefly, in patients who appear unresponsive, it affects how medicine approaches end-of-life care. For example, in organ donation after cardiac death, ethical questions arise about how long to wait before declaring irreversibility. If the brain retains residual activity for minutes after the heart stops, should protocols be adjusted? Similarly, pain management during the withdrawal of life support takes on new urgency if fragments of awareness may persist longer than assumed. These considerations show that studying consciousness at death is not only a philosophical question, but also a matter of medical responsibility. Beyond cardiac arrest, studies of comas and vegetative states also inform this discussion. Patients diagnosed as unresponsive sometimes show hidden signs of awareness when examined with advanced imaging. In one landmark study, a patient who appeared entirely vegetative was asked to imagine playing tennis while in an fMRI scanner. Astonishingly, their brain activity mirrored that of healthy individuals performing the same task, demonstrating covert consciousness. Though rare, such cases highlight the difficulty of assessing awareness at the edge of life. They suggest that consciousness can persist in forms that evade standard detection, reinforcing the idea that the boundary between life and death is less sharp than once believed. Cooling therapies, or therapeutic hypothermia, add another dimension. By lowering the body's temperature after cardiac arrest, doctors can slow metabolism and preserve brain function for longer. In some cases, patients have been revived hours after cardiac arrest, blurring the line between reversible and irreversible death. These medical successes show that the cessation of heartbeat and breathing is not an absolute marker of the end of consciousness. Instead, death is increasingly understood as a spectrum, from reversible cardiac arrest to irreversible brain death, with stages in between where awareness may flicker unpredictably. Nevertheless, limits exist. Brain death, the irreversible loss of all brain function, is widely recognized as the true endpoint of consciousness. Once neurons have undergone widespread necrosis, the patterns of activity required for awareness cannot return. Unlike cardiac arrest, which can sometimes be reversed, brain death represents permanent loss. This distinction underscores the importance of timing in resuscitation. If intervention occurs early enough, consciousness can sometimes be restored. If not, the emergent property of awareness is gone forever, even if machines keep the heart and the lungs working. Medical research also highlights the variability of experiences near death. Not everyone recalls visions or heightened awareness. Many report nothing at all, even after prolonged cardiac arrest. This variability suggests that the dying brain can take multiple pathways, sometimes generating vivid experiences, sometimes producing silence. Factors such as brain chemistry, pre-existing conditions, or the rapidity of intervention may shape which path occurs. Understanding this variability is a frontier challenge requiring larger studies and more precise monitoring. While near-death experiences often attract popular attention, it is important to emphasize that science approaches them with caution. Anecdotal reports, though powerful, are difficult to verify and prone to cultural interpretation. Still, they provide unique windows into human consciousness under extreme conditions. When combined with objective measures such as EEG and fMRI, they form a growing body of evidence that consciousness at death is more complex than simple absence. This medical frontier underscores a central theme. Death is not a single moment, but a process. Consciousness does not disappear at the instant the heart stops. Instead, it undergoes a transition shaped by neurobiology, metabolism, and intervention. In some cases, this transition includes vivid bursts of activity that feel meaningful to survivors. In others, it fades quietly without leaving memory. From a scientific standpoint, both outcomes reflect the dynamics of a brain in crisis, teetering on the edge of its ability to sustain awareness. The study of consciousness near death also reflects humanity's broader curiosity about existence. By examining the boundary scientifically, medicine turns personal mystery into empirical question. The answers are incomplete but advancing. We now know that the brain remains active longer than assumed, that experiences during clinical death are not uncommon, and that resuscitation science is pushing the boundary of what counts as reversible death. These insights do not tell us where consciousness goes after death, but show us how it behaves in the final transition. They reveal a spectrum rather than a binary, a fading rather than an abrupt end. What remains clear is that individual consciousness depends on the brain's fragile balance of energy and organization. Once that balance is irreversibly lost, awareness ceases. Resuscitation can delay or reverse the process temporarily, but not indefinitely. Eventually, entropy prevails, and the emergent property of consciousness dissolves. Yet studying this process scientifically enriches our understanding of both life and death. It shows that consciousness is not a static possession, but a dynamic state capable of extraordinary resilience and vulnerability alike. In this way, medical science does not diminish the mystery of death, but deepens it. The more we learn about the dying brain, the more we see how remarkable consciousness is. A fragile, emergent state that can flare brightly even in its final moments. Where it goes after death, in the strict scientific sense, is nowhere. It ends with the collapse of neural processes. But in its ending, it leaves behind echoes, in memory, in influence, and in the data that help us understand the most profound boundary of human existence. Neuroscience has mapped brain regions, identified neurotransmitters, and measured electrical activity with precision, yet no consensus exists on why subjective experience arises from physical matter. This problem, the so-called hard problem of consciousness, is central to determining what happens when the brain dies. If consciousness is merely the output of complex neural processes, then its fate is tied directly to the decay of the brain. If instead consciousness is fundamental to the universe or exists in some form beyond neural circuits, then death may not mark its absolute end. To examine this scientifically, we must explore the main frameworks that researchers and philosophers of mind have developed. The most widely accepted view in neuroscience is reductionism, the idea that consciousness emerges entirely from brain activity. According to this perspective, neurons firing in precise patterns generate perception, memory, and awareness. The mind is what the brain does. Under this framework, consciousness depends wholly on physical processes and ceases when those processes stop. Support for reductionism comes from abundant evidence: brain injuries that alter personality, drugs that distort awareness, and neural stimulation that induces artificial experiences. Each case shows a tight correlation between physical brain states and subjective mental states. From this angle, death is simply the irreversible end of the machinery that produces consciousness. The self disappears as surely as a flame goes out when its fuel is spent. Yet reductionism faces challenges. Correlation does not always equal explanation. Demonstrating that the brain generates consciousness does not resolve why subjective experience arises at all. This has led some scientists and philosophers to consider emergentism. Emergentism holds that consciousness arises when matter reaches a certain level of complexity. Just as liquid water has properties not present in individual H2O molecules, consciousness may be a property of complex neural networks, irreducible to their parts. The advantage of this perspective is that it explains why consciousness appears in humans, but not in simpler organisms. The drawback is that it still ties awareness to physical substrates. Once complexity is lost, such as through brain death, consciousness, as an emergent state, vanishes. A more radical approach is Panpsychism, which proposes that consciousness is not unique to brains, but a fundamental feature of matter itself. In this view, every particle or field possesses some minimal form of experience. Human consciousness, then, is not created from nothing, but built up from the combination of these fundamental conscious elements. Some modern physicists and philosophers, such as Galen Strawson and Philip Goff, argue that panpsychism provides a more coherent explanation of consciousness than reductionism, since it avoids the leap from non-experiential matter to experiential awareness. While panpsychism remains speculative and controversial, it offers a unique scientific implication. If consciousness is woven into the fabric of reality, then death may not be the end of consciousness per se, only the end of the particular organization that produced personal identity. What persists may be a dissolution back into more elementary forms of awareness, though not in any recognizable sense of the self. Another influential framework is information theory of consciousness, particularly the integrated information theory on IIT proposed by neuroscientist Giulio Tononi. IIT suggests that consciousness corresponds to the capacity of a system to integrate information. The more information a system processes as a unified whole, the higher its level of consciousness. Brains are highly integrated, which explains rich human experience. By this logic, death represents the disintegration of information processing, leading to the disappearance of consciousness. However, some researchers take the idea further, suggesting that information itself may be a fundamental entity, similar to energy or matter. If information is never destroyed but only transformed, as in physical laws of conservation, then consciousness, understood as informational structure, might not vanish but instead disperse. This view remains speculative but provides a bridge between neuroscience and physics in addressing the fate of awareness. Closely related to information theory is the idea of consciousness as computation. This framework, rooted in cognitive science and artificial intelligence research, treats the brain as an information processing system. If consciousness is the result of algorithms running on biological hardware, then its survival after death depends on whether those computations can exist elsewhere. biological death ends the brain's computation, but in principle, if the processes were replicated in another medium, consciousness might continue. While this raises questions about digital immortality or mind uploading, from a scientific standpoint, it underscores a key point. Consciousness may not be tied to matter itself, but to patterns of organization. Death then becomes the loss of one particular instantiation of those patterns, though the possibility of replication challenges the notion of absolute finality. Critics of these non-reductionist frameworks argue that they risk drifting from empirical science into speculation. Panpsychism, for instance, struggles with testability. How can one measure consciousness in an electron or a quark? Similarly, theories about consciousness as universal information may lack falsifiable predictions. For this reason, many neuroscientists remain committed to reductionist or emergent models, where evidence is clearer and experiments more feasible. Yet the persistence of alternative views reveals the depth of the problem. The nature of consciousness is not settled, and therefore neither is the question of its fate after death. Another perspective worth considering is the global workspace theory, GWT, proposed by Bernard Baars and supported by research in cognitive neuroscience. According to GWT, consciousness arises when information becomes globally available across different brain systems, much like a spotlight shining on specific data. Unconscious processes are like background workers, while conscious awareness is the shared stage. Death, under this model, extinguishes the stage. Without a brain to integrate and broadcast information, there is no spotlight, and thus no consciousness. However, GWT also reinforces the idea that consciousness is a process, not a static thing. This process can collapse gradually, raising interesting questions about transitional states during dying. Comparing these frameworks highlights a central tension in science, whether consciousness is dependent on the physical brain or fundamental to reality. Reductionism and emergentism argue strongly for dependence, implying that consciousness ends completely with death. Panpsychism and information-based theories suggest that consciousness may extend beyond the brain, persisting in some form even when personal identity is lost. Both approaches are scientific in that they aim to explain consciousness without appealing to supernatural claims, but they diverge sharply in their implications for what happens after death. It is important to stress that none of these theories currently has definitive proof. Each explains some aspects of consciousness while leaving gaps elsewhere. Reductionism explains correlations between brain states and mind states, but struggles with subjective experience. Panpsychism explains the ubiquity of experience, but struggles with testability. Information theory offers mathematical precision, but risks abstraction detached from lived experience. Consciousness as computation has predictive power in artificial intelligence, but raises philosophical puzzles about identity and continuity. This diversity of models shows how science approaches the question from multiple directions, converging on the recognition that consciousness is among the hardest phenomena to fully explain. The implications of these theories for death are profound. If consciousness is fully brain-dependent, then death is the absolute end of awareness. The self ceases completely, leaving no continuation beyond the decay of neurons. If consciousness is emergent, the end is still final, though it emphasizes the fragility of complexity. If panpsychism is true, some form of proto-experience may persist, though not the organized identity we call the self. If information-based or computational theories hold, then the patterns of consciousness may be preserved in principle, though not in the individual sense unless replicated. Each possibility frames death differently, not as a uniform cessation, but as an outcome shaped by the deeper nature of consciousness itself. This philosophical dimension of science underscores an essential truth. Understanding what happens to consciousness after death requires more than measuring neurons. It demands grappling with the most fundamental questions about what consciousness is. Until this is resolved, the fate of awareness after death will remain an open question. Yet the search itself has scientific value. By pushing the boundaries of neuroscience, physics, and information theory, researchers are expanding knowledge not only of death, but of life itself. The effort to explain consciousness at its ending teaches us about consciousness at its peak, during waking existence. Physics has long provided humanity with its most reliable framework for describing the universe. From the smallest particles to the largest galaxies, physical laws govern how matter and energy behave. If consciousness is part of the natural order, then it too must obey these laws. To ask what happens to consciousness after death through the lens of physics is to ask how energy, matter, and information behave when the brain, the physical substrate of consciousness, disintegrates. The answers offered by physics are stark in some ways and deeply provocative in others. The most basic law to consider is the conservation of energy, one of the most well-tested principles in science. Energy cannot be created or destroyed, it only changes form. When the brain dies, the electrical energy that powered neural circuits does not vanish. Instead, it dissipates as heat, chemical energy, and radiation into the environment. From this perspective, the energy of consciousness disperses back into the universe. However, this does not mean the subjective experience of being, the stream of awareness, continues. Physics distinguishes between raw energy and organized processes. Consciousness is not just the presence of energy, but the structured way that neurons channel it into patterns of thought. Once that structure collapses, the energy persists, but the phenomenon of consciousness does not. Here we encounter the second key principle, entropy. In thermodynamics, entropy measures disorder. Consciousness is an extraordinarily low entropy phenomenon, representing a highly organized arrangement of neurons, ions, and molecules. Life fights constantly against entropy, using metabolism to maintain order. Death is the moment when entropy overwhelms this process. Without circulation and metabolism, the brain's structures lose their delicate balance. Ion gradients collapse, proteins denature, and complex networks dissolve into disorder. From a physical standpoint, the end of consciousness is an increase in entropy, the natural return of complexity to randomness. Entropy thus provides a clear explanation for why consciousness ceases. The ordered state required for awareness cannot be sustained. Still, physics also opens doors to more subtle possibilities, particularly through the concept of information. In physics, information is not an abstract idea, but a measurable quantity. Claude Shannon's information theory showed that information can be quantified in bits, while modern physics connects information with entropy and quantum states. Crucially, just as energy is conserved, many physicists argue that information cannot be destroyed. When a system changes, information about its prior state is preserved in some form, even if scattered and nearly irretrievable. This principle, though debated, has been central to resolving paradoxes in quantum mechanics, such as whether information is lost in black holes. If information truly cannot be destroyed, then what happens to the information encoded in a person's brain at death? The trillions of synaptic connections, the unique patterns of neural firing, and the chemical signatures that define a mind. all of this is information. When the brain disintegrates, that information does not vanish instantly. Some is preserved in the arrangement of molecules, some in the environment as heat radiation, some in the causal effects a person has left behind in the world. This is not survival in the personal sense, but a transformation. The information that was once unified into a conscious self becomes diffused into the broader universe. From the standpoint of physics, death is the dispersal of organized information back into the sea of entropy. The relationship between consciousness and information has led some physicists and neuroscientists to speculate that the universe itself may be fundamentally informational. John Wheeler, one of the 20th century's great theoretical physicists, coined the phrase "it from bit," suggesting that physical reality arises from information at the deepest level. In such a universe, consciousness, if indeed it is a form of information processing, would be intimately connected to the fabric of reality. Death would then represent not an annihilation of consciousness, but a reconfiguration of information within this universal substrate. The self would still end, but the informational traces of its existence would persist, woven into the cosmos. Quantum mechanics complicates the picture further. In the quantum realm, particles exist in superpositions until measured. An entanglement links particles across vast distances. Some researchers, notably physicist Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that consciousness arises from quantum processes within neurons, specifically microtubules. This OR theory remains highly controversial and lacks empirical proof, but if true, it could imply that consciousness is not purely classical computation, but entwined with fundamental quantum states. In that case, when the brain dies, aspects of consciousness could, in principle, be released into the quantum field. Critics argue that the brain is too warm and wet for delicate quantum effects, but experiments in quantum biology, such as photosynthesis and bird navigation, show that quantum coherence can persist in biological systems longer than once thought. If consciousness has quantum underpinnings, death may not erase every trace immediately, but instead scatter quantum states into the larger field. Still, physics places hard constraints on these speculations. The conservation of energy and information does not mean the persistence of personal identity. When energy disperses, it does not retain the patterns that made an individual self. Similarly, when information spreads into the environment, it is no longer organized in the way consciousness requires. It is like the difference between a book intact on a shelf and a book burned into ash and smoke. The molecules and atoms remain, but the structure that carried meaning is gone. Physics suggests that while the ingredients of consciousness endure, the recipe that produced awareness is irreversibly destroyed. Cosmology provides an even broader perspective. Consciousness, as we know it, is a rare phenomenon in a universe overwhelmingly dominated by entropy. Stars burn hydrogen, galaxies collide, black holes evaporate, and in the far future, the cosmos trends toward maximum disorder. In this grand context, consciousness is a temporary island of low entropy, flourishing where complexity emerges. The death of an individual consciousness is part of the larger trajectory toward entropy. Even life itself will one day end, as stars fade and matter disperses in a heat death of the universe. From this cosmic view, the extinction of consciousness after death is not exceptional, but an expression of the same physical law that will eventually extinguish all structure everywhere. Yet within this inevitability lies an important point. Consciousness has already altered the universe by existing. Human awareness has produced science, art, technology, and culture. These outputs are not erased at death. They are material and informational imprints that persist, influencing the world long after an individual consciousness ends. Physics does not grant immortality to the self, but it does ensure continuity of influence. The actions of a conscious being ripple outward, encoded in matter, energy, and information that endure. In this sense, death marks the transformation of consciousness from internal experience to external legacy. Another physical perspective worth considering is the holographic principle, derived from black hole physics and string theory. This principle suggests that all the information contained within a region of space can be represented on its boundary, much like a hologram. Some theorists extend this idea to the entire universe, implying that reality itself is a holographic projection of information. If consciousness is information, then in principle, it is encoded in the structure of space-time itself. Death would still end personal awareness, but the information that constituted a life might be recorded at the most fundamental level of reality. This remains speculative, but it reflects how physics, when pushed to its limits, often blurs into questions of mind and existence. Skeptics argue that such interpretations risk anthropomorphizing physics. Information in the physical sense does not equate to consciousness. A decaying star contains information, but no one claims it is conscious. Likewise, the dispersal of brain information after death may satisfy physical laws without implying persistence of awareness. Physics, in its strictest form, points to a simple conclusion. When the organized matter of the brain dissolves, so does the phenomenon of consciousness. The energy remains, the particles remain, but the subjective experience ceases. Any suggestion otherwise requires careful separation between metaphor and measurable reality. Still, the dialogue between physics and consciousness research is valuable. By grounding the question in conservation laws, entropy, and information, science avoids speculation untethered from evidence. It shows that consciousness is not magic, but a physical phenomenon shaped by universal principles. At the same time, physics reveals the depth of the mystery. Information's apparent indestructibility, quantum mechanics' strangeness, and cosmology's vast perspective all suggest that the fate of consciousness is connected to the deepest laws of the cosmos. Even if the personal self ends, the structures it embodied leave traces in the universe that may never entirely disappear. In summary, physics tells us that the consciousness tied to a living brain ceases with death, because the structure required to maintain it is destroyed by entropy. Yet physics also shows that nothing is lost in the absolute sense. The energy and information that constituted a life remain, transformed and dispersed into the cosmos. Consciousness does not survive as a personal stream of awareness, but its physical traces ripple outward forever. The scientific challenge is to distinguish clearly between survival of the self and survival of information, between the continuation of subjective experience and the persistence of matter and energy. Where consciousness goes after death in physics is into the fabric of the universe, not as a mind, but as transformed energy and dispersed information, forever part of the cosmic story. Neuroscience shows us the brain as the cradle of awareness, its neural circuits giving rise to memory, identity, and subjective experience. Medicine reveals that consciousness does not cease abruptly, but fades through a complex process, sometimes producing surprising moments of awareness even as life ends. Philosophy of mind demonstrates that our theories of consciousness, reductionist, emergent, informational, or panpsychist, shape our interpretations of death. Physics, meanwhile, situates consciousness within the laws of energy, entropy, and information. showing both the limits of personal survival and the broader persistence of matter and influence. Together, these perspectives form a mosaic that is incomplete yet profoundly instructive. The neuroscientific evidence points most directly toward finality. Consciousness depends on the organized activity of billions of neurons communicating through trillions of synapses. Damage to even small regions of the brain can disrupt awareness, alter perception, or erase memory. This fragility underscores that consciousness is not an ethereal entity, but an emergent property of precise biological function. When the brain dies, the processes that sustain awareness, electrical signaling, chemical modulation, network integration, collapse irreversibly. In this view, death marks the end of the self, as decisively as the extinguishing of a flame. The overwhelming majority of scientific evidence supports this conclusion. Yet medicine complicates the picture by extending the boundary between life and death. Resuscitation science shows that consciousness can sometimes return even after minutes of clinical death, as long as the brain structure remains intact. EEG studies reveal organized bursts of activity at the threshold of death, hinting at brief windows of heightened awareness. Near-death experiences, though subject to interpretation, provide first-hand reports of vivid mental activity during clinical death. These findings suggest that death is not a sudden cliff, but a slope, with consciousness sometimes lingering, sometimes fading quietly. The endpoint remains the same, the permanent loss of brain function, but the path toward it is more intricate than once believed. Philosophy of mind deepens the discussion by questioning what consciousness fundamentally is. If it is fully reducible to brain activity, then its extinction with brain death is unavoidable. If it is emergent from complexity, the conclusion is the same. Once complexity collapses, so does awareness. But if consciousness is fundamental, as in Panpsychism, or tied to universal information, as in integrated information theory, then death may represent transformation rather than annihilation. The self would not survive, but its informational or proto-conscious components could remain as part of the fabric of reality. These perspectives do not change the scientific consensus that personal awareness ends, but they expand the scope of the question to include how deeply consciousness is embedded in nature itself. Physics provides the most expansive frame. Energy is conserved, so the energy of neural activity does not disappear. It disperses into the environment. Information, by many accounts, is also conserved, meaning the patterns of a brain may leave permanent imprints in the universe, even if scrambled beyond recognition. Entropy explains why consciousness ends. It is the unraveling of organized, low-entropy systems into disorder. At the same time, physics suggests that nothing is lost absolutely. The ingredients of consciousness endure, though no longer assembled into the living recipe that sustains experience. From a cosmic view, individual consciousness is a temporary configuration of matter and energy, remarkable in its complexity, yet subject to the same laws as stars, atoms, and galaxies. What science tells us then is that personal consciousness, your unique stream of thoughts, memories, and awareness, depends on the living brain and ceases when the brain irreversibly dies. There is no empirical evidence that subjective experience continues beyond this point. The vast majority of neuroscientific and medical findings converge on this conclusion. At the same time, science also shows that death is not an absolute erasure. The energy and information that constituted a conscious life are not lost but transformed, diffused into the environment and the universe at large. In this sense, while the self ends, the physical traces of its existence ripple outward indefinitely. This duality, finality for the self, persistence of influence, captures the scientific essence of death. Consciousness, as a personal phenomenon, ends with the brain, but consciousness, as a physical process shaped by energy and information, leaves marks that extend beyond the individual. Every thought, every action, every creation alters the world in ways that carry forward. Science does not promise immortality, but it does reveal continuity. The universe is not diminished by the end of a conscious being. It is altered by their presence, forever recorded in the patterns of matter and energy. The search for where consciousness goes after death is ultimately the search for what consciousness is during life. It forces us to confront the boundaries of neuroscience, to probe the mysteries of physics, and to reconsider the nature of information and mind. Though definitive answers remain elusive, the pursuit itself enriches our understanding. It teaches us that consciousness is both fragile and extraordinary, emerging from the interplay of countless forces, yet capable of reflecting on the universe itself. Death may end the personal experience of awareness, but it cannot erase the fact that consciousness existed, nor the transformations it set in motion. For a channel devoted to exploring the cosmos of the mind and universe, this scientific perspective offers both clarity and wonder. It grounds us in the reality that consciousness, like all natural phenomena, obeys physical laws. Yet it also reminds us that those laws contain mysteries still unsolved, about information, about quantum reality, about the true nature of mind. Science may not tell us that consciousness continues after death, but it reveals that consciousness itself is among the most remarkable emergent states the universe has ever produced. So, as we close this exploration, let us reflect on what science shows. When the brain ceases, personal consciousness ends, but the energy disperses, the information transforms, and the universe carries forward the traces of each conscious life. The story of consciousness after death is, in the strict scientific sense, the story of transformation, not continuation. And within that transformation lies a profound truth. By existing, by being aware, consciousness has already left its mark on the cosmos. With that, we bring this journey to a close. Thank you for joining tonight's exploration of science, mind, and the universe. Now, as you rest, may your thoughts drift gently, and may your sleep be deep and peaceful. Good night.